everyone. Thanks for coming out today. As mentioned, I'm Brooke. I'm going to be giving a talk, Love Potion number 9, Tar Pits, Purpose, and Keeping the Magic Alive. Really, the core idea in this talk, I think Dijkstra sums up really well. It's that computer science is no more about computers than astronomy is about telescopes. I don't normally do a lot of talks about my talks, but it seemed appropriate in this case. If you've ever seen one of my talks before, they tend to be deep dives, a lot of code, very technical. This one's a little bit higher level. Before I get started, I just want to say EMPEX is awesome. I've seen all of the videos from both coasts. Obviously, super honored to be here. Conferences are a ton of work to organize, as I discovered earlier this year. Big thank you to all the organizers for putting this together, flying us out. Just want to give them another big round of applause. And the whole conference circuit is extremely essential, right? This is where we exchange ideas, get people interested, force people to work on their libraries and clean them up right before their talk, and generally help Elixir win, right? So that's me. I'm XSpeed basically everywhere on the internet. I also apologize. I have a bit of a cold. I thought I was getting over it, but instead it's just moved down into my chest. This morning I woke up and I literally could not speak, so I drank 2 of these. I may have to take a couple water breaks during this, but anyway, I'm a programming language theory enthusiast. I founded a couple meetups in Vancouver. The most relevant to this talk is the Vancouver Functional Programming Meetup. And previously, for a number of years, I was an Elixir consultant, and I also taught teams. I've written a few libraries. Quark, Algae, and Witchcraft are the 3 that I'm probably best known for. Quark brings the really classic functional programming stack, the stuff from going back to the 40s, function composition and flip operators and all of that stuff. Algae is bootstraps up algebraic data types using structs, and Witchcraft is pretty much a wholesale port of the Haskell standard library. I did bring Witchcraft stickers if anybody wants them. They come in 3 delightful sizes. I've also written Exceptional, which is to make error handling feel more like railroad programming in Elixir, and Operator to help you define operators for your functions more easily. These days, I'm the principal engineer at FinHaven. We're a blockchain-based securities platform, so fintech. I don't really do so much in the fintech side of things. I'm a language designer. We're working on a language called Clarity, which is a high-level language, declarative language, so that regulators can read a language, and we can still do all the theorem proving and whatnot that you need when you're in a system where when you deploy your code, you can literally never pull it down, right? I'm also the co-author of a couple theorem improvement proposals, including token validation and the status code proposal. So it's a little bit rainy out today. I don't know if anybody was here earlier this week, but there was quite a bit of rain and I guess hail. So sorry for bringing the West Coast weather with me. This is what Vancouver looks like every fall, and yeah, including the trees. It's not great. My big themes today are where Elixir fits in the broader ecosystem, some of the underappreciated things that we're already doing and that I think that we could do more of, and then what I'm calling a call to curation. So, obviously I'm pretty into functional programming. I'd love to get everybody a functional programming job, but FP is sometimes a difficult sell, right? A few years ago, a friend and I decided we were going to be like the functional programming people in Vancouver. So we started a company, Robot Overlord, and try to sell companies on the idea. And it was difficult. So we thought, well, let's go with, Vancouver's pretty, Ruby-centric, so everybody's excited about Elixir. Let's go with Elixir. Selling developers on Elixir, not a problem, right? Selling companies on Elixir, surprisingly difficult, right? Now, I think there's a number of reasons for this, and that's actually a good chunk of this talk. The good news is that the popularity is growing, right? So these are the Stack Overflow questions. So methodology here, sure, fine, but we're down below the 0.4% of the questions. Just kind of clean that up a little bit. It looks something like this. Go did really well, right? They were launched in '09, and pretty much just right away, just boom, right? Everybody's using it. Elixir took a little bit longer, a couple years, right? First real public release 2011, took about to 2014 to even register on this chart, but it's definitely this this upward angle, right? Unfortunately, Elixir's not perfect. I said it. Feel free to pelt me with rotten fruit. When we try to sell Elixir, it's often, Ruby and Erlang had a love child, and we called it Elixir, right? We have this Ruby-inspired syntax. People will sometimes try to sell it as it's just like Ruby, but faster, right? No, it's just the syntax. We have this great Ruby-esque culture, right? Which, that's why you're all here, right? I don't have to sell you on that idea. We have this battle-tested VM and ecosystem, which is great. We have these Lispy semantics, and sometimes people give me kind of like Elixir's not a Lisp. And you're right, it's not, but it's actually the underlying way it works is surprisingly similar. We're starting to pull in other things too, like mixed format, which Go is currently popularizing. Formatters are interesting. They were all the rage like 30 years ago, and then people dropped them, and now they're back. So we'll see how this plays out in the long term. On the downside, Elixir doesn't really bring a whole lot new to the table, right? It's sort of collecting different things from other languages and other ecosystems. There is this anti-Ruby prejudice. There's a reason that there's all of these Ruby refugees, right, coming into Elixir. If you say, well, it's just like Ruby, well, then why are you not using Ruby, right? We don't have the huge ecosystem. High availability is no longer unique, right? There are other ways of doing this. It keeps getting called niche, and I think this is because it's a functional language, and it's not one of the the top 5, let's say, in usage. And the really big point is that people keep trying to sell this on the syntax. When I'm running the meetup, people will say, yeah, it's got this really nice syntax, I really want to use it. It's not about that, it's about the semantics of the language. So you've probably seen this spectrum before. It's imperative versus declarative, right? And languages get laid out roughly like this. So on one far extreme, we have assembly. On the other extreme, we just have English and everything in between. And kind of in the center and slightly off to the side, we have all of our functional languages sitting here, which is kind of weird, right? Because these languages don't feel anything like each other. I think it's better demonstrated this way. So we have three points on our triangle. In our bottom right, we have languages that are focused on operational semantics, how things evaluate, how the machine works. We have a dynamic view of the world because we have some global state that we're updating. We're changing the way that we run based on this global state, right? It's a very mechanistic model, right? Do this, then this, then this, then this. And again, roughly these languages, right? Bottom left, we have denotational semantics, the mathematics, things that are universal. I want to be able to say, for all integers, this holds true, right? Again, roughly these languages, and this is also anything that we do with induction, so running on lists, let's say, right? And in the top, we have languages that are linguistic, which is very meta, and they're worried about the context and the the semiotics, what the symbols mean, like literally the symbols mean, as opposed to some other model. And roughly these. And there are more, but for the purposes here. There's been a very clear historical trend. Now, it doesn't go just in one direction, right? We have Rust and Go are kind of further down in this on the triangle, and they're relatively new. But overall, over the past 60, 70 years of programming history, we've been moving from working right raw on the metal up to something that's readable, right? Obviously, as humans, we want something that we can understand and read, and it just does what we want it to, right? There was a theory in the 80s that there were different generations of languages. Functional languages were this 4th generation, and we're going to move into this 5th generation that were these constraint logic programming languages like Prolog and Minicanren and things like that. That never really materialized. We've seen a little bit of it, especially with things like SQL. But that didn't really happen. But again, the overall trend has been going from bottom to up on this triangle. I think the big main insight, the main win of Elixir, the reason people get so excited about it is because it takes something like Erlang and pushes it significantly further up on this triangle and just slightly to the right, right? You end up thinking a little bit more operationally in Elixir than you do in Erlang. It sits on that chart right next to a Lisp or two, and I've mentioned before that has these Lispy semantics. I'm not going to go into too deeply. I'm just going to show you that now this is not Lisp-flavored Erlang, but if we just replace the do and ends with parentheses and move them to the outside, it becomes very Lispy very quickly. Now it's not quite as dynamic as a traditional Lisp, but honestly, there's almost a one-to-one correspondence, which makes sense, right? We have a homoiconic language. That's how it should work. Pipes are skin deep, which it's not a bad thing, right? It's actually really great. Makes things very clean, easy to follow. We can design systems. You see this done a lot in Elm, where you sort of ignore the pipes and you can just read it like English, which is fantastic. And yeah, it makes no difference to the underlying evaluation model, right? But there are trade-offs. Now we're stuck in this mechanistic mode of thought that you're going to do this, then this, then this, then this. So even though it's a functional language and we're being, even if it's totally pure, we're saying these are the steps that we're going to follow. It does clean up a lot of code, but it means that we're not grouping things by ideas anymore. We're grouping them by how the machine is going to think through the problem, right? We do get the really nice compositional zoom effect, right, where you can stick a bunch of functions together, zoom in, deal with the details, zoom back out, right? Phoenix, a lot of people describe Phoenix this way, that you have your controller, and then you can dive into the controller and see how it breaks down, right? The zooming effect doesn't really apply that well to actors, right? It's only specifically for pipes. And there's no reason that it couldn't. We're just not working at that same level of abstraction. Complexity. There's no way getting around it. Again, you've probably seen this stack before. I've added 2 extras to it. The top level is the user, because you can absolutely push the complexity out to the user. And network, which is the literal, where do your servers live aspect. And there's potential complexity everywhere, right? You can't get away from it. You have to sort of choose where it goes. In Elixir, we tend to put it at the application level with the developer, or down in the network, right? And we have tools for helping this be easier, but we do a lot of stuff at the network level, so we end up pushing it into there too. So trying to sell people on all of these ideas, where it sits in the language ecosystem, all the kind of cool things that it does, selling my little heart out, trying to preach Elixir, and people will always come back with, other than Node and Ruby, we'd love it if you could use Go, which seemed odd at first, but it kind of makes sense, right? It makes sense that Go's eating our lunch. It's also fast, familiar, and concurrent. It has this traditional programmer mindset. It's much more imperative. We have this very traditional FP mindset, but it's still in kind of an imperative way. They're both very familiar to, well, the design constraint on Go was to be familiar to recent CS grads. In Elixir, has ended up being mostly people who already have industry experience, but not necessarily in a functional language. Go, on the other hand, has a very well-defined philosophy about what it's about, right? It's this near-the-metal, garbage-collected language that is about concurrency, specifically, right? It's about going fast, right, over a networked system. It's very, very simple at the language level. Almost everything's done in your application or at the network level, right? Very little abstraction, almost none, right? This can also lead to be very error-prone, right? Due to having to hand roll all of your functions, you end up needing an architect on Go projects because it's not baked into the language for you, right? And actually, this description isn't that far off of Elixir either. So there's this thing called the Turing tar pit when you have these very simple languages. Because simplicity isn't simple, right? There's a trade-off somewhere. There's an old saying that any sufficiently complicated imperative language is an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. I would say here it's more that any sufficiently complicated imperative program is all of that of a more abstract language. Functional programming is not immune. We have the church tar pit, right? You can go right down to lambda calculus and work through every step of trying to encode numbers as lambdas, and there's a whole scale here. So explicit state, which obviously we have a lot of in Elixir, means that there's a lot of explicit state handling. You have to pass the world around all the time. You could push it out into an agent, but typically we don't, right? We just pass things down through. And this causes a focus on the mechanics of how we're going to do things rather than the underlying concepts, right? I don't know about you, but when I'm designing a system, I walk up to a whiteboard and I start drawing pictures, right? I don't start writing code right away. Luckily, we can describe these general solutions with abstraction, right? Which is what lambda calculus is. I'll just try to keep going. Lambda calculus is this, right? We really just have three things in lambda calculus. We have lambdas, which are abstraction. We have naming, which is your alphas, and reduction, right? Application. That's all that we have. Is really we just have abstraction. We can use abstraction to make large things feel small, right? Because now we have a better tool to work with it. Fewer patterns to memorize because you're not working with the individual little pieces all the time. You're working with ideas. A nice concrete example that I like to give for this is for loops versus reduce. Reduce is great. It's beautiful, right? It's a general solution for what a for loop does. We don't have to worry about, well, I have this global state variable, and I'm going to run through it and update it, and I have to make sure that I'm so far in the list or the array. No, we just say enum.reduce with this thing, boom, general method, done, right? It makes it much more declarative, right? Once you know what reduce is, you can use it basically anywhere. Simplicity has a cost, right? We either wind up with complexity in the large, or you end up with the DSL, one or the other, right? I've personally been burned by a couple old Erlang libs that were under-documented, all the possible error states that they could have, and arity, returning tuples with different arity, and blowing up randomly in production. It got to the point where we just wrapped this thing in a rescue block, and prop tested it until we figured out what all the possible error states were, right? We tried to look into the library, but a lot of the error tuples were coming from different places and just getting threaded through, and it was just really hard to trace through. So, yeah. Actor model is often said as, this is an organism, right? So I'm saying that, well, things can be complex in the large, but every step in the actor model is very simple, right? Well, this is also a system with every step is very simple, right? This is breaking down sugar. Reasoning about dynamic organisms can be very difficult, right? You have to in OTP, right? We have to remember to store our data for if it does crash and we have to restart that part of the system. It may be lossy, right? Just because we have high availability doesn't mean that we haven't lost that request, right? And there are techniques for keeping the data around, but it's not a guarantee, right? And you have to remember to do this. So this is, again, at the application level. Now, I think Phoenix and Flow do amazing jobs of this, right? You don't, unless you want to, you don't have to worry about this in a Phoenix app, right? Flow cleans up. I think GenStage is fantastic in its own right. Flow makes it just so nice and so declarative to work with. You don't have to worry about all of the little details, right? It just works. So this is really about having tools of thought. Thinking at all and language at all both require abstraction. Right? You are the same person over time, right? If you're totally concrete, there's only you at this time point and then another time point. These are separate instances. No, we've decided that we have an abstraction of a continuity for a person, right? Or any object. We're no smarter than our ancestors. Abstraction, I don't actually know how they came up with this idea, but abstraction seems to appear about 50 to 100,000 years ago. And it's, as time goes on, we just end up with better tools, right? So, example I like to give is, if anybody's ever tried to do arithmetic with Roman numerals, it's painful, right? There are some parts of it that are really easy, right? Doing addition and subtraction, well, you're just, losing little, ticks. That's easy. But if you want to do something more complicated, it gets hard fast. When we're using Arabic numerals, we have all these techniques that we just learned in grade school that were considered really hard, cutting-edge things not that long ago, right? Even things like having 360 degrees, the way that it is set up, we've broken it down in such a way that we have all of these nice divisors, right? If it was in, instead just say 1,000 or something, we wouldn't be able to break it into thirds as easily, right? Our mental tools tend to come in two flavors, right? We have abstractions and algorithms. So just pure concept and ways of doing things. Algorithms have actually outpaced hardware in a lot of domains in terms of just raw performance, right? Which shouldn't be surprising, right? If you've ever looked at different sorting algorithms, vast differences in performance, right? So even though we do need a base level of hardware performance, the way that you approach a problem and the concept that you use change things dramatically, right? And this is especially important with Moore's law ending. We've had some major successes in the last couple of years. Obviously, machine learning is just exploding, right? These are things that we could not just brute force on a decision tree, right? We decided to change the model, look at things probabilistically, and suddenly we are beating people at Go and have self-driving cars and all of this stuff, right? The other one, obviously, I kind of live in this blockchain world. There's things called snarks, zero-knowledge proofs. So right now, if you want to get on, say, Ethereum, you have to first download 30 to 40 gigs of blockchain, run it all through, because it's essentially an event source system, run through it, get the current state, check that the state matches, and now you can make a transaction. With snarks, you download something that's a couple K, that's it. And you don't have to do any extra proving. You just know that this is the right one because of the way the algorithm works, right? So I'm going to be using some specific definitions here. We have two axes. We have specific versus general, and concrete versus abstract. And we tend to live more or less along this one line. So specific concrete thing is me right here, right now. An abstract general thing is like community or love or these very intangible things that are very, very broad. You can have something that's abstract and specific, like a number, a specific number, right? I can talk about 42 or 3 or the letter A in a very sort of specific way, as if it was concrete. And then we also have things that are general and concrete, like all the speakers at this conference. We tend to live roughly in this range. It would be nice if we could just sort of expand where we're working in programming a little bit past this oval. Right? So there's some abstraction sweet spots that we can aim for. And there's this, this range, generality versus power. General things have very low information. We don't make any assumptions whatsoever, but they apply to pretty much everything, right? Things with high power tend to be very specific. You can really tailor your solution, but you only hit a couple use cases. So as example, the enum module is very general, right? We just have solutions for how to work over things that can be converted down into lists, right? We don't say anything about what's inside those lists or that other data structure. We just say, this is something that you can work over top of. Something with a lot of power is ecto.schema, right? You have this very declarative, DSL for doing things with a database, right? Describing a database. It's very, very clean, very succinct, but you can't really do a whole lot else with it, right? It's really just for this one use case. In the middle, right, there's a couple of sweet spots. The first one that I have to mention, because I'm the author of Witchcraft, is monads, which get maybe more credit than they're due, but the main reason people talk about them so much is because they precisely capture the idea of what it means to be Turing complete in a number of contexts, not just in just a pure function, right? We can have Turing completeness in a system that may fail, and it can fully capture that idea. One from more the standard library is GenServer, right? It's not totally general, it's not totally specific, but we can do a lot of stuff with it, right? So it kind of hits this sweet spot again, right? This is another thing that we can really sell to people is we've hit this sweet spot. General things tend to end up in libraries. Powerful things tend to end up in applications. And you can always make general things more specific by applying things to them. Right? You can't really go the other way around. That's much harder. So there's some other sweet spots. Embedded DSLs, really nice. Certain combinator designs, right, like certain sets of functions do really well. I swear this is not ancient Egyptian algebra. I'm actually curious, does anybody recognize this language? Yes, excellent, great. APL has, depending on the exact implementation, has about 60 symbols, 60 functions, and they don't write libraries, right? They just have idioms, right? So they remember the 4 characters it takes to do something, and then they just write those 4 characters. Right? It's shorter than writing import this thing. Right? So in APL, a lot of things are more powerful than the sum of their parts. The abstraction that they found is really doing matrix operations and vector operations, which is great because that's how modern computers are laid out as linear algebra. You can do lots of stuff with it. Right? This is Conway's Game of Life. That one-liner is all of Conway's Game of Life in APL, right? So let's give a more concrete example in Elixir. I'm going to not give all of the code to do this, just in interest of time. Something I found that I want to do a fair bit is I'll be, going down a series of pipes, and I get to one point that I'm like, well, geez, I really wish that I could just memorize this one part, put it somewhere, and continue down with my piping, and maybe do some other stuff to this, this memoized value, and then bring it in at the end, right? So I end up breaking it out into two series of pipes, right? And then taking that value, using it again in the next one, right? And sort of breaking it up. So this is a bit of a contrived example, but again, just trying to keep it small, where we have some input, and I want to put it down two paths, one doing, division, finding a position in a string, and the other one building up a string from the same value, and then getting, a certain letter from this string. So I can do this sequentially, or I can do this in parallel, or at least concurrently. Obviously, these have the same structure. I've had to write this twice. There's no code reuse whatsoever, right? Lots of duplicate code. And I'm limited to two ways now, because I've hand implemented it twice, right? So instead of this, how about we describe what the overall solution should look like, and then later decide how it's going to get run, right? So let's think about this geometrically, right? This is how these graphs are usually written, left to right. I have some input coming in, I split it. I send one down this lower path, the other one gets split again, has some stuff done to it, brought together, and I get my result back out. This is one way of doing it, and here's how the colors line up, right? I can even lay it out. If I rotate my graph, I can lay it out the same way. Let me tell you, the formatter does not like this, right? Now, this is just sticking, doing function composition. That's the strange operator, the unfamiliar operator in there. And this is a concept called arrows in witchcraft, which also means that you have to understand arrows to get here. And arrows are very, extremely abstract. How do we model it a different way? Well, I can separate my specification from my execution by putting in a struct. Here's those same functions. They're now sitting in these structs. And this is just a tree, right? And I can then later pass this tree down into an interpreter, which will then run my computation for me, right? But also because it's a tree, trees are mappable. So another nice thing in functional programming, and especially when you have a pure function, is that you don't have to make the distinction between programs and functions, right? Your programs are functions, your functions are programs. So we can see them as functions from programs to programs, right? So in this case here, I have io.inspect. This is the same tree as before, and I need to do some debugging on it. I want to inspect each part of the tree as I run through it later, right? So I can just map over it, io.inspect, and we will append to each leaf of the tree io.inspect automatically. And now when it runs, we will automatically get all of those printed out, right? With a one-liner, right? We can clean this up a little bit, make it a little bit more DSL-y. Some macros. This is, again, all the same stuff, just a little bit cleaner looking. And then we can also make this into a protocol so that we can now have the interpreter portion of this. So the default version of this is going to be the sequential one. I'm going to say that when I split, it's two sides of a tuple. And when I unsplit, I'm going to have some function that sticks two sides back into one. When I run this on 45, I'm going to split that into the two sides. One goes into this first function, the next one goes into that, into function of y, and then at the end we stick them together. Pretty straightforward. I think pretty readable. We can create an async wrapper for this, and just some helper functions, asyncify and syncify, to wrap and unwrap this. And then write our versions for split and unsplit. And it looks basically the same. I just have to put the value in and out of my async version, and suddenly it all works the same, So what's the upshot? We have a much higher semantic density, right? We don't have to worry about the mechanics, we're worried about the semantics. Super extensible, right? We can make a version of this for Flow and it'll work. Right? You just learn the concept once and you can use it all over the place. Because we can guarantee certain things about the synchronous and asynchronous code where they overlap in their meaning, we can test the protocol implementation, and then in our application, testing async code can be hard, just test the sync code, right? And we can combine abstractions. So earlier we had this specialized tree. There are lots of tree libraries, right? We could just reuse the trees. Purposeful languages. Haskell has this motto right from the beginning called avoid success at all costs, right? The purpose of Haskell is not to be the language everybody uses. It's to get ideas out into other languages. Right? And they were very explicit about this back in the early 90s. Languages like this, like Rust and Elm, are very clear about their messaging, what they're for, who their target audience is. Elixir doesn't really as much have this clear reason, right? I was talking to Robert Verding a few months ago, happened to be passing through Vancouver, and I was asking him, what was the genesis of Erlang? How did that all work? He's like, well, we happened to land on functional programming because of our design constraints. We happened to design the actor model. They didn't even do that intentionally. Somebody later in a paper wrote, they're using the actor model. Like, what's the actor model, right? So what's even a good pitch for Elixir? And it's not, it's kind of like Ruby, right? I want to say that Elixir is the best of all worlds, and that in order to get there, to say this with absolute confidence, we need to do a little bit of ecosystem work. Right? Great artists steal, right? I say that we should be about curation over creation. We don't have to come up with the big ideas. We should just look around what everybody else is doing, find out the cool stuff, bring it into Elixir, make it feel like Elixir, and I think we'll just win, right? Concepts, patterns, and practices. We're already doing a lot of this, right? I think we need to drop saying the Elixir way. This is a holdover from the Ruby way, right? We need to get back to the core principles of the language, which is being pragmatic, right? Which is about making things that are hard feel easy. But we still need to focus on that Elixir feel, the feel of Elixir. People are so thrilled and happy when they're writing Elixir, right? I have people coming up to me at the Vancouver meetup all the time, and I'll mention like, oh yeah, I'm doing this talk about Elixir. Oh, you're doing a talk about Elixir, right? The feel of the language is just so fantastic, and we can't lose that if we're just importing random stuff from other ecosystems. Right? This is a little bit like what Apple does, right? Apple doesn't actually invent anything. They just refine it down, right? They're focused on consistency and feel. They have this super loyal following, and there's an app for that. I want us to get to the point that there's a lib for that, right? And I want all of these libs to be to work together, right? I want to say Elixir is about ideas. We curate great concepts and practices. We just need a few more atoms in the atom smasher right now. Right? We need to be conceptual omnivores, right? Go out, explore with other languages, other ecosystems, and bring back the cool stuff. Make more Elixir, right? We're already doing a lot of this. I've mentioned GenStage and Flow a few times. I think that they're fantastic. Same thing with Phoenix. I think it does just like absolutely beautiful job. The core team is doing a just fantastic job of making these things feel easy, right? And they don't always feel easy. These aren't things that we've invented. These exist in lots of other ecosystems. We're just doing honestly, I think a better job of it, right? We're doing it with intention, right? If we break the abstractions down at the right places, we'll get mix and match. Just like I was saying before, like these are just trees. Why not, right? We can leverage all the other work that people are doing in the ecosystem. And there's so much more we could do. I could do an entire talk on what else we're doing, or what else we could do. But here's just a couple ideas off the top of my head. Proof and constraints, so that you don't need runtime checks, right? You can put a precondition in front of each of your functions that you're expecting your input value to be multiple of 2. You can do this right now with a when. But why not wrap that in something else that then says, okay, well, these all say that this needs to be a multiple of 2. This one says it has to be a multiple of 4. Let's just take all of those and stick it up here in the tree, and now we never have to check it again, right? Once we have these constraints, we can do interactive development. We can start having an editor. There's a few systems that do this already. Idris has an emphasis on interactive development. There's also in the scheme world, Barleyman, which is still somewhat experimental, but you have these constraints, and it can start solving constraints with implementations for you, right? So you start typing like, I want to do kind of this thing. It's like, does this chunk of code work? Like, yes, it does. Thank you. And I'll just change the things that I need. Now, this can get tricky, right? In Scala, there's these 2 camps. Java without the braces and Haskell fan fiction. And the 2 don't really talk to each other that much, right? And there's this people are afraid of, well, if I use cats or Scalas, I'm going to have to convert my entire app. And in some cases, like not always, but in some cases that's true, right? It's not totally compatible, right? You can do some mixing, but it can get painful, right? It's such different styles, such a different feel. So we're going to propose 3 laws of language extension. 1, context independence, right? The most fundamental. Each unit of code should be able to be taken by itself. 1 + 1 should always equal 2, right? You might have something in a do block that's changing something about how the flow is happening. That's fine, as long as each line works the way I expect it to, and it doesn't affect the stuff outside of it, right? Just like how we have hygienic macros. Same idea. Ethos. I want this to still feel like Elixir, right? This shouldn't feel like something else. This shouldn't feel like C. It shouldn't feel like Haskell. It shouldn't feel like Scheme. It should feel like Elixir, right? Unless it conflicts with the context independence. And lastly, completeness. Don't just throw one function in there, right? Just like, we'll just add a flat map, right? There's a reason that a lot of these ideas get grouped together in these other ecosystems, right? Because we want them to work, they're systems, right? Just like how in APL, we had 60 or so symbols, and we get all of this power out of it. If we had 2 of them, in fact, we do have some of those in Elixir already, and we just don't get the same synergy out of it, right? So as much as possible, add everything that you can into your library, break it out into its own thing so people can reuse it, unless it conflicts with the top 2 laws. So join me in this noble quest. Let's build the world's greatest ecosystem. Let's curate great concepts, keep the feeling, ensure that everything's interoperable, and keep winning. Thank you. Woo. Thank you, New York.